So today we would like to study to discuss photochemistry of the cyclohexenone 4,4 disubstituted cyclohexenone. This is actually alpha beta unsubstituted cyclohexenone, alpha beta unsubstituted system, 6 members. When we have a system like this is your alpha beta unsaturated cyclohexenone, and here it has been found that this system gives a very interesting photochemistry when the fourth position 1, 2, 3 and 4 fourth position is disubstituted, whether it is R or AR, aryl group or a alkyl group. So whenever we have a system like this where the 6-membered cyclohexenone system, alpha beta unsaturated cyclohexenone system, and 4th position is disubstituted, whether it is a dialkyl 4,4, and that's why it is written here the photochemistry of 4,4 disubstituted cyclohexenone, or whenever we have a system whether the 4,4 dialkyl substituted or 4,4 diaryl substitute alpha beta unsaturated cyclohexenone, it undergoes a very interesting photochemistry, and as this 6-membered ring under photolytic condition has been found to give a bicyclic system where with a 5 plus 3 ring system. So this rearrangement has been observed when cyclohexenone is substituted at 4th position disubstituted. Now let us see what is the product when we have a we'll just take 2 examples here, 4,4 dimethyl cyclohexenone and 4,4 diphenyl cyclohexenone, and under photolytic condition what is the product and what are the steps involved in these reactions. This is the rearrangement. When this is alpha beta unsubstituted cyclohexenone, the 4th position is disubstituted, is the 4,4 dimethyl cyclohex 2-ene, and when under photolytic condition it undergoes a very interesting rearrangement giving rise to a bicyclic bicyclic system consisting of 5 and 3 ring system, as well as the substituents remain the same. So this looks very interesting because a 3-membered ring is constructed, and the construction of a highly strained system such as 3-membered ring is not very easy, and that's why this rearrangement has attracted lot of interest, and at different examples with different substituent has also been observed. Is a similar example here as well when the 4th position is substituted with a diphenyl group. It is also an alpha beta cyclohexenone. 4,4 diphenyl cyclohex 2-ene under photolytic condition undergoes similar type of rearrangement giving rise to 5 plus 3 system where the 2 phenyl groups remain the same and the same. So this is the starting material, and this is the product after the rearrangement under photolytic condition. This is a starting material for diphenyl substituted. This is the product, and hence this is a very interesting rearrangement, and the steps involved can be for the formation of this product can be visualized as it is. So this is the first system. Here we have taken the diphenyl substituted system, and then diphenyl alpha beta is a starting material which we have just discussed. 4,4 diphenyl cyclohex 2-ene known under photolytic condition. This is the product 5,3, and the steps involved. We know that under photolytic condition this is a mechanism of the formation of this product. First step is excitation of this carbonyl. Say for example, if you write this gets excited giving rise to a diradical species, and then And then since there is a double bond, and whenever we have a radical adjacent to a double bond or a cation or an anion, it delocalizes, and we can write a delocalized structure as it is, as shown over here. So this is the first step is excitation of the carbonyl pi star and delocalization, giving rise to 1, 2, 3 and 4, 1,4 diradical. And when we have the next carbon is substituted with the diphenyl group, so this undergoes now this diradical in the case of enone system. In the case of enone system, the diradical species has been has a very good evidence that this diradical is converted to dipolar species or zwitterionic species. Deuteronic species or a dipolar species. So since this is a specialty in the case of enone system, when in the enone system when we generate a diradical, it has a very good evidence that diradical species is converted to zwitterionic species, or you can call it a dipolar species. So as shown over here, so this diradical is converted to the dipolar species of zwitterionic species. The presence of this this in the photolytic condition in the case of enone system like this, it has a very good evidence, and there are these dipolar species have been trapped by different trapping agents, and hence it has. So first, excitation of the carbonyl, the delocalization to generate 1,4 diradical, conversion of 1,4 diradical to a dipolar species, 1,4 dipolar species, and then this undergoes rearrangement. So this is a this undergoes a ring contraction to give a more stable carbocation. So this carbocation is rearranged to a more stable carbocation, and then this rearranges negative charge of O minus comes back, and this double bond can attach, and then it gets this. So these are the steps involved in the formation of this photochemistry of 4,4 disubstituted cyclohexenone system. Whenever fourth position is disubstituted either with a methyl group or with a phenyl group, it gives and rearranges to give a 5 and 3 membered ring. It has a very interesting and very good rearrangement, because in this rearrangement 6 membered ring is converted to a bicyclic system consisting of 5 and 3 membered ring. The steps involved are as follows. First one is under photolytic condition, excitation. Under photolytic condition, it gives a diradical species, and this radical is in adjacent to carbon-carbon double bonds is transformed to a 1,4 diradical, and then 1,4 diradical in the enone system is converted to a dipolar species or a zwitterionic species, and this a positive charge on the secondary carbon, the H here, is converted to more stable tertiary carbocation. So this carbocation is converted to more stable carbocation through the ring, through the bond contraction, or it phase 6 membered. So this the rearrangement takes place, and then O minus comes back, and then the attack of the double bond to give this product. So this is the product form in the case of bicyclic cyclohexenone system where 4,4 disubstituted, where the 4 position of the cyclohexenone is substituted with either alkyl group or an aryl group. So same as the here what we have seen is the phenyl group. If we have say, we'll just discuss this later. If we have a dimethyl group, this can also undergo a similar type of rearrangement. So for example, this is a dimethyl CH3 alpha beta unsubstituted 4,4 disubstituted cyclohexenone under photolytic condition, excitation of the carbonyl to give a 1,2 diradical, and then 1,4 diradical. This radical is adjacent to a double bond delocalization and transformed to another 1,4 diradical. And then the diradical species in the case of enone system has a very good evidence to converting or transforming into a dipolar or a Zwittonic species. So this gets converted to O minus and the positive charge on this CH3, and now this carbocation is transformed to a more stable carbocation through the shifting of this double bond. So this gets so this is the O minus, and then we get a positive charge on here, and then the CH3 here, and then this is transformed to the product by O minus coming back, converting to carbonyl, shifting of the attack of this double bond to attack of this double bond to this carbocation, and then we end up with the a product like this CH3. So we can see that cyclohexenone alpha beta unsaturated systems with a 4,4 disubstituted cyclohexenone, whether there is a methyl group or 4 position or an allyl group 4 position under photolytic condition, undergo very interesting rearrangement, giving rise to a 5,3 system. And the first example with the phenyl substituted we have seen here. So this is the when we have a dimethyl substituted 4 position or similar condition can give rise to. The steps involved are as follows: excitation of the carbonyl to generate 1,2 diradical. Since there is a double bond, can transform to a 1,4 diradical. 1,4 diradical has in the case of enone system has a very good evidence that this diradical species is transformed to a dipolar species or a Zwittonic species like this, and then this carbocation is transformed to a more stable carbocation through the ring contraction bond shifting, and then the conversion of the O minus to transform to the carbonyl, and then attack of the double bond to this. So this is a very interesting rearrangement in the case of cyclohexenone. People have tried a lot of example has, and few of the bicyclic system. See, this is the heading bicyclic alpha beta unsaturated. So this is example. So instead of a monocyclic, is a bicyclic system. Bicyclic alpha beta unsaturated cyclohexenone. Photochemistry of bicyclic alpha beta. This is alpha, this is beta. Alpha beta unsubstituted. Photochemistry of bicyclic alpha beta unsaturated system, alpha beta unsaturated carbonyl system. So like this. So so far what we have seen is the monocyclic enone system with a 4,4 whether it is a R or AR or a phenyl group, as of course with the phenyl group. So 4,4 diphenyl or 4,4 dialkyl in the case that transforms to a product like this. So if we have a phenyl, so of course, so people have just looked into the what happens when we have a bicyclic system. So under photolytic condition, as usual, we can generate 1,2 radical and then transformer 1,4 under photolytic condition, the excitation of carbonyl n pi star and to 1,2 radical and then transform to the to a more stable 1,4 radical. 1 2 3 4 1 4 diradical species, and then we have just now mentioned that in the case of enone system, transformation of a diradical species to a dipolar species the troinic species is well known, and then this carbocation is now transformed to a more stable carbocation. So there is a methyl group in the ring junction. So this transforms to a more stable by shifting of this bond. So ring contraction. This is a 6-6 system. This is again 6-6 system. Now it's going to be a 5-6 system. And now now this carbocation is now rearranged. O minus comes back and generates a carbonyl here, and the shifting of the double bond here, a ring contraction of this. So you have a 5-5 system. So this is again very interesting rearrangement when we see bicyclics, alpha beta unsaturated carbonyl system with a methyl group at ring junction, and we start with a 6-6 ring system, striated system. Now it has gone to a 5-5 system, and you can see a lot of rearrangement has taken place, and the steps are very simple under photolytic condition. First step, as we mentioned, 1,2 diradical transform into a 1,4 diradical, 1,4 diradical going to a dipolar species, which has been found to be very common in the case of enone system. This carbocation is transformed to a more stable carbocation, and through the shifting of this double bond, and then this undergoes rearrangement. O minus goes back to generate a carbonyl, shifting of the double bond, and then contraction of the another 6-member ring to give a 5-5 ring system. So this is again you can see a very nice rearrangement in this particular case as well. So going further, so we have seen alpha beta unsaturated ketone. And now what happens when we have a cross conjugated? So this is a system. We have a alpha beta unsaturated as well as a conjugate. So this is a cross conjugated system, cyclohexadienone. Photochemistry of cyclohexenone. We have a cross conjugated of carbonyl, alpha beta unsaturated, alpha beta. This is also but is with the 4,4 disubstituted system. So this is again we have a diphenyl, or we can also have a dialkyl as well. You can see here is a cross conjugated alpha beta unsaturated with a dimethyl or disubstituted. So this rearrangement takes place under the condition that the fourth position has to be disubstituted either with a dimethyl group or a diphenyl group. So steps involved will be as usual, as we have seen earlier, the excitation of the carbonyl to give 1,2 diradical, and then which transform to a 1,4 diradical because of the presence of a double bond at alpha beta position. This is a 1,4 diradical, and then this transform to a and of course to another radical, or we can directly transform this to a zootronic species. So this goes to a ring contraction to give this 1,3 diradical, and then transformation of this to a dipolar species. Dipolar species O minus and plus, and then this gets rearranged, O minus converting to the carbonyl, and then shifting of the double bond and the cleavage of this bond. And of course it is a it will not be just to, for sake of understanding, I have just shown that when it generates, it opens up, what happens, how it will generate a negative charge, and there is already positive charge which will combine to this. But essentially it is a simultaneous reaction, and then this goes O minus, goes back, converting to carbonyl, shifting of the double bond, and then this goes and attacks here, and then we get this product. So you can directly go this. This is just taken for the understanding, just to make it understand that this, when this bond cleaves, generate a dipolar species, but it will definitely take place under simultaneously cleavage as well as forming of double bond. So the cyclohexadienone, cross conjugated cyclohexadienone, again with the 4,4 disubstituted cyclohexadienone, cyclohexadienone ring system. When we have a cross conjugated, whether it undergoes a similar type of rearrangement what we have seen in the case of 4,4 disubstituted cyclohexenone with an alkyl, with the aryl group as well as alkyl group in the previous cases. Here what happens when we have a cross conjugated? So under photolytic condition, as usual, we have 1, 2 and then 1, 4 diradical, and then transforming to another diradical, or it can through a ring contraction, there is a formation of a cyclopropyl group, and then goes to a 1,3 diradical, and then transform into a dipolar species, 1,3 diradical. There is a dipolar species, 1,3 dipolar species, and then is rearranged to the products O minus, converting to double bond, shifting of this double bond to this, and then this goes and attacks on this cation, cleaves, and then goes and attacks to this to give this product. So it has been found that whether we have a either phenyl group or a methyl group in and the system is cross conjugated, we have a similar type of rearrangement as we have seen earlier in the case of the cyclohexenone. So cyclohexenone 4,4 disubstituted either with alkyl group or with aryl group, or the dienone having a cross conjugated with the 4,4 disubstituted with either alkyl group or with a aryl group, undergo a similar type of rearrangement, giving a 6-membered ring going to a 5 and 3. Here also 6-membered ring going to 5 and 3, and hence it has a very good rearrangement because it leads to the generation of a 3-membered ring where it is a highly understained, and construction is not very easy in the case of construction of 3-membered ring stain system. And here we get one of the product, a 3-ring plus 5-ring system. A monocyclic is converted to a bicyclic. Monocyclic converted to a bicyclic ring system. Here also a bicyclic has a 6-6 has converted to 5-5 ring system we have a, and here also is a monocyclic 6 is converted to a bicyclic system in the case of. So this rearrangement has been exploited by taking different examples such as bicyclic cross conjugated. So when we have we have seen a bicyclic only a alpha beta unsaturated acetone. Here people have also tried to bicyclic with the ring junction methyl group, a cross conjugated. What rearrangement takes place in this particular case, that will continue on the next lecture. Thank you very much.